Ni hao. Hello. This is the 20th lesson in heat transfer. In the 20th lesson, we will begin the unit discussing internal flow convection heat transfer. There are 3 parts to the 20th lesson. In the first part of the lesson, we will discuss why it is important that we study internal flow convection heat transfer. I will try to answer the question, why should you care about internal flow convection heat transfer? By the end of this lesson, you should be able to provide an example of a relevant engineering system to which internal flow convection heat transfer applies. You should also be able to explain what a parabolic trough solar concentrator is and how it works. On with the lesson.
Internal flow convection heat transfer. I want to try to motivate you a little bit. This is a picture. This is actually a very famous picture now, turns out. Didn't know it was going to be famous at the time it was taken, I bet. Of a man standing in front of a parabolic trough solar concentrator. So that man I happen to know him, good friends with him actually. It's Dr. Richard Diver. So he's worked with us on some of our solar work, and he graduated from the same school as I did for PhD, for his graduate work, out of essentially the same laboratory, the Solar Energy Laboratory at the University of Minnesota. So I know Rich really well. He's a West Point grad, loves to hike, retired now. And he spent a career thinking about how to make concentrated solar better. And this is a picture of him in front of a test concentrator at Sandia National Labs. And then behind, what I like about this picture too is this is their parabolic trough test unit. But behind them, you can see also their parabolic dish systems operating. And Rich also worked on these systems. They're actually Stirling engines sitting at the focal of these parabolic concentrators. And those Stirling systems that he worked on actually still today hold the record, the world record, for the most efficient conversion of sunlight into electricity. It's over 40%. Of course, they were redonkulously expensive, but and so they haven't really panned out, but they still hold the record for the highest efficiency of converting sunlight into electricity, better than any PV panel or module. So how these parabolic trough concentrators work, you have sunlight that comes in and it's reflected down to an absorber, and in that absorber you have a heat transfer fluid that flows. So we're seeing internal flow convection heat transfer inside of the absorber. So this is the idea. Sunbeam comes in, it's reflected by the parabola mirror onto the absorber, and inside of this, the absorber is actually inside of a glass envelope. Why would that be? Yeah, Alex?
The light can get through.
So the light can get through, but of course, if we didn't have the envelope there at all, it would still get through. I mean, that's true. Chase?
Doesn't glass like plankton rays or something like that?
No, so the glass is actually so glass, of course, is transparent to the visible, but and we're going to talk about this more when we get into the radiation unit. But it's not like, perfectly transparent across all wavelengths. So it actually cuts out quite a bit of long infrared radiation, but we still put them on there. But doesn't really have anything to do with the radiation side. From the radiation perspective, putting a piece of glass between the light and the absorber is bad. We're actually cutting out some of the available energy right there. So there's another reason we put the absorber in a glass envelope. Daniel?
Keep away from the outside air.
Yeah, we want to reduce convection heat transfer to the ambient air. So we put it in a glass envelope to lower the external flow convection heat transfer, right? Wind is going to blow over that absorber tube. That's bad. It's going to suck energy away that we worked really hard to put in. So that's why we have it in a glass envelope. And actually, the really good systems pull a vacuum between the absorber and the envelope. So you actually have very low pressures in that space. So you're also, again, trying to cut down on the convection from the outer surface of the absorber tube to the glass envelope surface. But on the inside of this, we have fluid flowing through that absorber tube. And so you've got heat transfer happening, right, off of the inside surface of the tube into the fluid. And the idea is that we're going to heat that fluid up, and then you pass it through. You can see in your handout, you know, lots and lots of these parabolic trough collectors. And you can get the temperature of the fluid up to, some of these parabolic trough systems get the temperatures of the heat transfer fluid as high as 550 C. And then we take that high temperature and essentially we use it to produce steam and drive a steam turbine and produce electricity. So understanding what designing these things, you have to understand the internal flow convection heat transfer in order to size the tubes. And get the temperatures that you want. Like predicting how temperature is changing along the flow length is important. Understanding what the overall heat transfer rate is important. You have to have passed, undergrad heat transfer to design these systems, I guess. So a little bit of motivation if you want to think about a problem that applies here for internal flow heat transfer. Also external flow, right? Because we had to know something about the external flow heat transfer to say we should probably put a glass envelope.